So today I am starting the topic the gradient. So before starting the gradient, let me tell you a little bit about the fields. What is this field? So the field is so if we have a space, okay, so if we have a physical quantity like let's say we have a physical quantity and we is like the temperature, okay. So if we have a body and we can actually measure the temperature of that body, okay, while field is the any physical quantity is not necessarily located or distributed over a one region of a space. Like here, this body, the temperature of, we are just measuring the temperature of this particular body, okay, and not the environment. But the field is actually the measurement of physical quantity over all space, okay. So we can first of all we can have a temperature field. So what temperature field is? Let's say we have a temperature field denoted by T, which is a function of x, y and z. So it may be any function of x, y and z. So what it represent? It represent the value of temperature in the space with the coordinate x, y and z. And once we put the once we take a value x, y and z and plug that x, y, z in this temperature, so we will get a value, okay, the scalar value, and that scalar value is representing the temperature at that coordinate, okay. So this temperature field is actually a scalar field, okay. So we have a field, it can be a scalar field, like for example temperature. We can have a vector field, okay. So we have a vector field just like example electric field, okay. So what is electric field? So electric field, this E can be represented it is a field, so it can be represented by Ex, which itself may be a function of x, y and z, and this is the x cap, plus Ey, that itself may be a function of x, y and z, plus Ez, that itself may be a function of x, y and z, okay. So that is the vector field, okay. So we have a coordinate x, y and z. So electric field, once we take a particular point in space which has a particular coordinate x, y and z, so at that point when we plug the value of x, y and z in this three the function, then we will get the electric field with the different all three components, okay. So at this point there will be an electric field represented by this arrow vector. But if we look at the other point, here the electric field may be different, their magnitude and direction may be different. So all over the space this field is actually the electric field has different values, different directions, okay, and this whole thing is represent what we call the electric field, or in general what we call the vector field. In the similar way we can have a tensor field. So what is this tensor field? Although we will see it in the tensor course, so tensor field generally comes it comes in one of the the physical application of the general theory of relativity. So it is represented by G of u and mu. So it is a tensor field represent in some sense the Einstein's gravity, okay. So instead of just like we have vector with three component and this component varies according to x, y and z, in the similar way this Einstein gravity tensor, whatever we call, is the common the real name is actually the metric tensor, okay. So this G nu mu is actually the representation of this this g nu mu. Actually what it does, it has, instead of this 3 component, it has 16 component, and in the 16 of the out of 16 only 10 are the independent component. Okay, the rest are just the repeating component. Okay, so this actually represent the gravity in the Einstein general relativity. So g nu mu is actually can be written as in the metric form. Okay, so we have this 1 2 3 4, and what is why they 4? One is the time component. We have included the time and the space on the same footage in the general relativity. So it will look like this. It is a function of x, y, z and t. It may be a function of x, y, z and t in general. So this tensor field works in this way. Okay.